Hello everyone, in today's video I'll be discussing DNF block. Whatever paragraph is there, I'll be just giving a summary of that and moving on with the important points. So in the first paragraph, we have absolutely nothing except what is incomplete D subshell, what is the definition of a transition metal, and what is regarded, what is not regarded. Second paragraph, we have again we have absolutely nothing. So from the paragraph, the fun starts. So they have given that PD has 4D105 as 0, and that's why what do you say? Except for that, the general configuration is fitting the rule. Okay, then they have done nothing except give us the first series, second series. So first series, I'll just be telling out the names of the. I mean, first series we all know. Second series, I'll be writing down over here. Yttrium. Okay, first. Wait 1 second. Okay, yttrium is like this. Yttrium. Okay, then zirconium. Like this. Then we have niobium, like this. Then we have molybdenum. No, 1 second. Let me think. Yeah, molybdenum. Then we have technetium. Oh my god, 1 second. Technetium. Technetium. Then we have your infamous ruthenium. Ruthenium. Then we have your rhodium. We have your rhodium. We have palladium after that. Palladium. And then we have silver, which is like this. And then cadmium. Okay, cadmium. Then if you talk about your 5, sorry, we'll talk about the 5s2 and 4d. Okay, 5s and 4d electrons, how many they have basically. So I'll just be drawing this quick table. So yttrium has 2 4 5s and 1 4d, 2 5s, 2 4d, 1 5s, 4 4d. Okay, 1 5s, 5 4d, 1 5s, 6 4d, 1 5s, 7 4d, 1 5s, 8 4d, 0, 10, 1, 10, 2, 10. That is your order of your elements. Then we'll be moving on. Then this common in text question we have to discuss. Ag2 is the most common oxidation state of Ag, and that has partially filled orbitals. So that's why it's that's why it's a transition element. Then typical metallic properties they're displayed. Mn, everything except Mn's, all the the weird ones, the last ones which are not considered your what do you say? What do you call the transition elements? Except that and Mn. Okay, Mn को mug up करना है बस. So then melting point order, if you look at, we'll be going just by the graph. WMOCR peaking. Melting point is peaking at this point. Peaking. Alright. MNTCRE. It's kind of getting lower. Except for this one. We can say that TC and MN, it is getting lower. That's like the lowest almost. Okay, if you look at it, it's almost the lowest. Okay, so we'll be talking about that. So TC and MN mainly, not RE. Then summarizing this paragraph, this huge one, we have more down the series you go, more down the series you go, more the atomization enthalpy, like more down as in you go more rightwards. Basically, that's what I meant. More the atomization enthalpy, more the nobleness in reactions. Okay, they are noble in their reactions. As you go more right, they become less reactive. They are more noble in their reactions. And if you notice the graph, okay, it's very similar to your melting point. First 3 pay you have a peak, then it again goes down, like it goes to fucking hell. So we can say that this is scandium, titanium, vanadium, chromium, manganese, like that. Correct? No? So yeah, somewhat like that. I mean, order though it's there in the table, I'll tell you. So they have said why this actually is very low. It's because F electron or D electron की shielding तो बात करें तो F electron is worse shielder than the D electron, so that's why the radius decreases a lot. It's almost same of this. Size of 5f orbitals decreases along the series. वो भी पता है because you're adding more electrons, so न्यूक्लियर चार्ज तो डिक्रीज हो गया। टी आई टू सी यू, टी आई से सी यू तक डेंसिटी तो डिक्रीज हो जाएगी, आई मीन इंक्रीज हो जाएगी, बिकॉज मास बाय वॉल्यूम, and you put your logic. Enthalpy of atomization, vanadium has the highest, Mn has the lowest, and Ni is also pretty high. Matlab, we can say that. So order goes to be scandium to vanadium, it increases. Vanadium to manganese decreases. Manganese till nickel increases. Nickel till zinc decreases. Okay. Over here, we can notice that the order of the IE1. Uh, See, it goes like this graph: increase, decrease, decrease, decrease. Clearly, your IE1 of Fe is pretty high to be very legit. Let's just check the order given by the. One second. We'll check the order given by the NCRT before viewing other sources. Yes, guys, Fe is one of the highest. So this order comes in legit, but this a zinc part, it should come a little higher if it's there. So it decrease, increase, 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 decrease, decrease, increase. So we can say that Ti to V it decreases, V to Cr it increases, Cr to Fe it increases, Fe to Ni it decreases, and then Ni to Zn it increases. So it's a weird order. I won't be. Hopefully, I don't have to remember it. Metallic radius order. It just nicely. It's a pretty good decrease, I would say. Matlab, on the left to right, it's decreasing, except for your Mn, which has a increase. Okay, Mn randomly has an increase. Then you have Fe, Co, Ni, Cu. Cu also it starts increasing. Cu, Zn. As far as I know, I don't think this is important. So let's move on to the rest. M2 plus order, Cr is equal to Mn, is greater than Fe, is greater than Co, is greater than Ni, is less than Cu. M2 plus M, um, basically, yeah, this is all okay. I hope so. Lowest atomization enthalpy is this. Enthalpy of atomization is something that you might need to remember. Then, a little bit, we have ionization enthalpy. In this paragraph, we are just summarizing that second ionization enthalpy increasing values is expected in second ionization enthalpy. Um, and yeah, shielding effect, so we know basically. And the three factors that it required is responsible for the value of ionization enthalpy is attraction to nucleus, repulsion between electrons, and the exchange energy. Exchange energy is the stabilization energy when the electrons of a degenerate orbital have same spin. Okay, so basically, and they're saying D6 loss of exchange energy at D6 configuration is not there, and they also saying loss of exchange energy increases the stability. But then basically we know all these common sense stuff, right? High values for third ionization enthalpies of copper, nickel, and zinc indicates why it's difficult to obtain oxidation state greater than 2 for these elements. Okay, so it can be noted that only up till Mn we have oxidation state more than 3. After that, I mean, it's pretty rare to find compounds or stuff that have oxidation number more than 3 for greater. Cr3 plus is also very common because of like because T2G be there. T2G is there, guys. So that's why we have to explain that. And yeah, so here we can say that titanium 4 plus is more stable than titanium 3 plus 2 plus. फिर भाई rather abrupt decrease in stability of higher oxidation state after MN वो तो बता था. And then yeah, that's all right. Here they have said that MO46 plus W6 plus is more stable than what your CR6 plus. Okay, basically lower oxidation state is preferred in P block, but in D block, heavier members prefer your higher oxidation states itself. Okay, basically, higher oxidation states is preferred by higher, like bigger members of D block, heavier members of D block. So yeah, that's why. And then low oxidation states are found when a complex compound has ligands capable of pi acceptor character. Um, in addition to the sigma bonding. Okay, NiCO4, FeCO4 oxidation state of nickel and iron is zero. Then you have M2 plus to standard potential. Cu has inability to liberate H2, only oxidizing acids, nitric and hot concentrated sulfuric react with Cu. Okay, basically the acids also get reduced over there. It's not balanced by its high hydration enthalpy. That is the reason that everybody knows. And Zn are more negative than expected from the trend. For Ni related to its highest negative delta hydration, that is what E is related for Ni, but for E not for your Zn and Mn, it is related to the D10 configuration or D5 configuration. Then stability of V2 plus can be explained. I think any stability when there is T2G stable, right? When the T2G stable, that's when you call the stability of that. So CrF6 tetrahalides and all, they are also stable. MnO3F2 F is known. MnO3F is a known compound because it is giving out a seventh oxidation state of Mn, and it's not represented in simple halides. That also we know, right? KMnO4, right? KMnO4 minus, it's showing Mn at 7 plus. So yeah, that's one of your oxygen compounds. For halogen, maximum is MnF4. I'm pretty sure MnF4 is your highest in your this thing. So one thing that we always forget is that VX3 plus H2O gives VOX3, which is a very what do you say? This thing, very pleasant thing to see. And COF3, why is a fluorine able to stabilize COF3 is because of high lattice energy and high bond enthalpy terms for the higher covalent compounds. Like for example, VF5, CRF6, it has very high covalent character. So hence proved, done. It's over. How covalent character is directly proportional to anion size, right? So I mean, you get the point. Basically, higher covalent compounds such as VF5, CRF6, they have high more this thing. Cu2 plus halides are all known except the iodide, because iodide gets very disproportionated. Like basically, what happens is that your Cu2I2 will be forming actually instead. So yeah, because Cu2 plus oxidizes I minus 2I2. Okay, that's the reason. Copper 1 plus compounds are unstable in aqueous medium, and they undergo disproportionation. Okay, so Cu plus becomes Cu2 plus and Cu. So that's something that we always tend to miss. See, they said beyond group 7, no higher oxidation oxides of Fe per Fe2O3 are found. All right. Yeah, so but FeO4 2 minus is formed in alkaline media, guys. Remember, please remember this. FeO4 2 minus is formed because Fe4 plus is also possible. 6 plus is also possible state for Fe. It's written over here, guys. It's a very missed point that I must say, it's a very, very missed point that Fe6 plus exists. So FeO4 2 minus will also exist. All right, so that decomposes to Fe2O3 and O2. So one thing about chemical reactivity and E naught values that we tend to miss is that um, actual rate of them reacting with oxidizing agents like hydrogen ion is very slow. Like titanium and vanadium, in practice, they're passive. Okay, they're passive to dilute non-oxidizing acids at room temperature. Ti and V are passive to H plus, even though 3D series is highly reactive. Okay, and they have copied these lines from before. E naught values for Mn, Ni, Zn are more negative than expected. Okay, and for Mn2 plus and zinc, we know because of the D10, D5, but for nickel, it is delta E is related to the highest negative enthalpy of hydration.